Hello everyone, this is Kavita here from India. Currently I am teaching in a leading institute of Kolkata, Swami Vivekananda Institute of Science and Technology. There is a query from a student studying under Maulana Abul Kalam Azad University of Technology. The query is about the definition of Fourier Transform. He has noticed in a textbook written by Dashpal. This book is followed by different institutions under Maulana Abul Kalam Azad University of Technology. In this book, in the definition of Fourier Transform, he has noticed that the positive power of exponential is used. Simultaneously, he has noticed in another book written by Speisel, the negative power of exponential is used in the definition of Fourier transform. Now his question is that which one should be used? Let us try to understand both the exponential forms, positive power of exponential and negative power of exponential, using the software Mathematica.
What is Fourier transform? The Fourier transform is an useful tool to analyze the frequency components of the signal. Or we can say Fourier transform convert signal in time domain to frequency domain by integrating over the whole time axis. If ft represent a function with tangent nature and finite energy content, Fourier transform represents such a function as a weighted sum of exponentials at different frequencies. Here is the question about positive and negative frequencies. As if in equation 1, negative frequency is used and in equation 2, positive frequency is used. Now, after his query, the question becomes, does negative frequency exist? What is the difference between positive frequency and negative frequency? Why in some books in the definition of Fourier transform, positive frequency is used and in some books negative frequency is used? And so on. Let S be non-negative frequency. The sign of S is preserved in the complex valued function e power ist we know cos st plus I sin st. This is the real part and this is the imaginary part. The real part and imaginary part can be separately observed and compared. Let us observe this using the software Mathematica. y1 equals to exp ist. Say s equals to 4. z1 equals to real part of y1. Now plot z1 t from 0 to 10 Okay, we got it. Next, Z2 is imaginary part of y1. Plot Z2 t is same 0 to 10. Got it. Next, let us take y2 as exp minus ist. Okay, s has been taken same as before. Now z3 equal the real part of y2. Okay, now plot z3 t is same from 0 to 10. Got it. Now z4 is imaginary part of y2 and plot z4 t is same from 0 to 10. Got it. Okay, now look here that the real part for both e power ist and e power minus ist obviously same, and the imaginary part of e power ist and for e power minus ist different. In the complex plane, this is real positive axis and this is imaginary positive axis. So in the complex plane, positive frequencies rotate counterclockwise. If omega is the angular frequency, positive frequency rotate counterclockwise. Whereas negative frequency rotates clockwise. A pair of complex sinusoids with opposite frequencies can combine to form a real sinusoid. If we write here cos omega t, then it is half of e power I omega t plus e power minus I omega t. Here we have taken cos st as half of e power ist plus e power minus ist, which gives rise to the interpretation that cos st comprises both positive and negative frequencies. Physically, the frequency is positive because frequency is the number of events per unit time. Though mathematically negative frequency is defined, any measures that includes both frequencies includes a false or alias. Because frequency can have only one sign. The Fourier transform, for instance, merely tells us that cos st cross correlates equally with cos st plus I sin st as with cos st minus I sin st. Nevertheless, it is sometimes useful and mathematically valid to treat this as the combination of two different positive and negative frequencies. So most well-known application of negative frequency is the Fourier transform. Fs is integration from minus infinity to infinity, ft e power minus I st dt. This is the convention that we use the negative in the definition of the Fourier transform. This measures the energy in function ft at frequency s. When evaluated for a continuum argument of s, the result is called Fourier transform. For this definition of Fourier transform, the inverse Fourier transform will be ft equals to 1 by 2 pi integration minus infinity to infinity fs e power ist, mark here it is positive, ds. Now if someone writes the definition of Fourier transform against the convention fs equal minus infinity to infinity ft e power positive ist dt, in that case the inverse Fourier transform will be 1 by 2 pi integration minus infinity to infinity fs e power minus ist ds. I will show you one very interesting result from Fourier integral theorem. We know ft equals to 1 by 2 pi integration minus infinity to infinity integration minus infinity to infinity f u cos alpha t minus u d u d alpha. Say equation 1. Now we know that sin alpha t minus u is an odd function. So the value of this integration is 0. Say this is equation 2. Multiplying equation 2 by I and adding to equation 1, we get ft as 1 by 2 pi integration minus infinity to infinity integration minus infinity to infinity fu cos alpha t minus u plus I sin alpha t minus u du d alpha. Now we can write this as fu e power I alpha t minus u du d alpha. So we can write this as 2 pi integration minus infinity to infinity e power I alpha t d alpha integration minus infinity to infinity e power minus I alpha u du. What is this? Fu. What is this? This is nothing but the definition of Fourier transform. Fourier transform of Fu. So we can write that as integration minus infinity to infinity f alpha e power I alpha t d alpha. What we were using? We were using that ft is 1 by 2 pi integration minus infinity to infinity fs e power I t ds. Now if we multiply the equation 2 by minus I, then we will get here the negative sign and we will have this as fu e power minus I alpha t minus u. Then in this position we will get negative sign and this one we will get positive sign, and then we will get the inverse Fourier transform as 1 by 2 pi integration minus infinity to infinity f alpha e power minus I alpha t d alpha. So both the results you are getting. Let us conclude the query. Equation 1 is the prevailing definition of the Fourier transform, where equation 2 is the inverse Fourier transform. In some books, however, equation 2 is described as the definition of Fourier transform. This is a matter of convention. For instance, positive angle is measured along anti-clockwise direction. This is a convention. Yet aspirants, be careful about some textbooks and popular lectures where Fourier transform is defined against the prevailing convention.